Earlier in the semester, we talked about transforming both absolute value equations and quadratic equations. And when we talked about that, we talked about the different transformations that we could apply to those functions. We talked about shifts, either horizontal or vertical shifts. We talked about compressing or stretching our function using a scaling factor. And we also talked about reflections. We can apply those same three basic types of transformations, translations, stretches, or reflections, to any polynomial function. So let's take a look real quick at just the basic form of a transformation. We said earlier in the year that we could take, again, any function that we wanted. Here's our function f in this case. And we could apply one of those three basic transformations, one or more of those three basic transformations. We could shift horizontally by our factor of h. We could shift vertically by our factor of k. And then we could also stretch or compress our function by the factor a. And we also said that if a was negative, then that would also be not just a stretch or compression, but also a reflection. So again, we can apply these same ideas to the polynomial functions that we've been discussing. We can apply them to cubic polynomials, to quartic polynomials, to polynomials of any degree. The one difference now, though, is that you cannot create any given polynomial using these translations. What that means is that if your degree is greater than 2, so this does not apply to a quadratic, but if you had a polynomial, let's say just the basic cubic polynomial or the basic quartic polynomial, we cannot create any cubic polynomial or any quartic polynomial just using these three basic transformations. What we can do, though, is we can still take our parent functions, either y equals x cubed, or y equals x to the fourth, or y equals x to any other power greater than 2, and we can still shift those parent functions around and apply the three basic transformations given by this general form here. Really, the only difference that I'm trying to tell you about is that when your degree is greater than 2, you can't create any given cubic polynomial, for instance, or any given fourth degree polynomial. There are only a few, a smaller set that you can actually create using these three basic transformations. So let's do an example. All right, let's say that we want to apply some of these transformations to the parent function y equals x cubed. And in this particular example, the three transformations we want to apply is a shift 2 units to the left, a shift 4 units down, and a stretch by a factor of 3. So to create this, we just apply the same methods that we applied earlier in the year when we were shifting either absolute value functions or quadratic functions. Our new transformed equation we can construct by applying each of these three transformations separately. If we want to shift 2 units to the left, that's going to be a horizontal shift. So that's going to be x plus 2, and then we're going to cube it, because again that's what's being applied to x. If we're shifting 4 units down, that's what's being applied to y, so that's outside the function that's being applied to x. That's going to be minus 4. And then finally, if we want to stretch by a factor of 3, that was our a value from the general form we saw on the last slide, so that 3 is going to go up front. That 3, if it's a stretch or a compression, that means that we need to be multiplying by that factor. So here's our transformed cubic polynomial, 3 times the quantity x plus 2 cubed minus 4. Clearly this is not written in standard form for a polynomial, but if you wanted to write it in standard form, you would simply need to cube this binomial x plus 2, then multiply that result by 3, and then subtract 4. All right, let's do one more example of this idea of transforming polynomial functions. Let's say we want to construct a quartic function. Remember that quartic means fourth degree. And we want this quartic function to have two real zeros, and only two real zeros, one being at x equals negative 2, and the other being at x equals positive 1. That means that the function, of course, will only have two x-intercepts, one at x equals negative 2 and one at x equals positive 1. Because of the fundamental theorem of algebra, however, we know that if we have a fourth degree polynomial, there have to be 4 zeros. If 2 of them are real, that means the other 2 must be imaginary. So let's go ahead and see how we can construct this polynomial. There are a few methods that you could use here, but I think the easiest one is to say, alright, well, we want our polynomial to have a real 0 at x equals negative 2, so that means that I know the factor x plus 2 must be a factor of my polynomial. We also want another real 0 at x equals 1, so that means we also know that the factor x minus 1 must be a factor of our polynomial. And then we need 2 other zeros, but they need to be imaginary. And so actually here you get to make the choice what you want this last factor to be. There are lots of infinitely many correct answers here. You just have to choose one that would result in 2 imaginary zeros. The easiest factor that you could plug in here would be x squared plus 1, because of course if you set that factor equal to 0, just go ahead and do that real quick. If you set this factor equal to 0 and solve for x, then of course you get x squared equals negative 1, which means that when you take the square root, you get x equals positive or negative I. So there would be our final 2 zeros for this particular quartic function that I created. You don't necessarily have to choose x plus 1 to be your final factor, though. I could have said, x squared plus 1. I could have said x squared plus 4, if you'd rather do that. But your life will be easiest if you just choose this last factor to be x squared plus some easy to work with number. So in this case, if I set that last factor equal to 0, so we get x squared plus 4 equals 0. To solve for x, I of course subtract 4, so we get x squared equals negative 4. And when we take the square root of both sides, we're going to get x equals positive or negative 2i. So again, we've got those 2 imaginary zeros that correspond to our 2 real zeros. Let's go ahead and leave x squared plus 4 as our final factor. Again, that last factor is completely up to you. If we want to go ahead and write our polynomial function in standard form, then of course we're going to have to do a little bit of multiplication. So I'm going to go ahead and multiply our the first 2 binomials together first. I'll get x squared plus x minus 2 times the binomial x squared plus 4. And then just doing a little bit more multiplication, I distribute the trinomial to the binomial. So we'll get x squared plus, not x squared, x to the 4th, plus x cubed minus 2x squared, and then plus 4x squared plus 4x, ran out of room, minus 8, and last step would just be to simplify this. So for the polynomial that I constructed that will have real zeros at negative 2 and positive 1, I've got the polynomial x to the 4th plus x cubed plus 2x squared plus 4x minus 8.